important to actually define what these things mean, what the engineering simulations are, and then what kind of data I'm actually interested in and I'm talking about. So let's talk about engineering simulation first. So the idea is, why are we interested in engineering simulation? What they are and why are we interested? So I'll give you an example that has nothing to do with turbulence. I won't talk too much about turbulence today, so I want to give you examples that are much broad and perhaps easier to connect to. So this is, you know, an unfortunate situation, but something obviously we can all relate to, you know, a crash. And as you can imagine, the most important aspect of this event is to make sure the person that is inside the car or the people that are inside the car are safe, right, in spite of the accident. And it turns out that today, to design this system, and a car, any car actually, you have to go through safety checks and you have to pass certain criteria before actually, as I said, you can even produce the car, you can even put the car in production. So it turns out that for many years now, rather than sort of hoping that the outcome will be successful in this case, so that, you know, nobody dies in a sense, in addition to sort of designing, there have been very, very carefully planned and carefully carried out crash tests. So you go in a laboratory where you're actually controlling, this is a real vehicle, but it goes through a certain scenario of a crash where you have a lot of measurements, where you have, you know, actual mock-ups of individuals in the car, and you actually assess, you know, various metrics. So it turns out that obviously this helps tremendously with understanding what happens in the real case, but it is extremely expensive to do this. You're actually building a vehicle that is exactly the same that you wanna produce beforehand, and then you're crashing many of them, you're testing them, and so on. So it's clear that if we could use computers to build virtual crash scenarios, we could do many, many more of those. We could start doing it well before any of the actual vehicle is actually built. And we can study much more about perhaps design choices that we have to improve the outcomes of these kind of virtual crashes before even building or even cutting any metal. So this is what sort of the goal of engineering simulations are, sort of complement real, perhaps laboratory tests to inform what happens in real events, right? And obviously, the crash is just an example here. Obviously, if you're interested in jet engines, you can imagine how much you can simulate of that jet engine before putting it together to study a lot of performance of that system itself. Now, one of the questions, or some of the questions we have to ask ourselves are this, you know, are the simulations, this kind of simulation accurate? Do they really predict the real-world outcomes? Are they really sort of connected in some way to this kind of scenario? That is what we care about. Or they just look good, and they simply look like they're real. You know, think of a video game, right? In that case, if they look real, it's good enough. Nobody's going to die anyway. But in this case, apart from, you know, your virtual self, but nothing sort of happens in real life. But the question is, if you want to really connect to the real accident, and you want to avoid doing some of these crash tests, you need to know how accurate those are so that you can actually replace some of the tests. So that's the big picture. Now, in what I do, and Ronnie mentioned Cascade, which is a sort of a commercial arm of some of the research that we do at Stanford, we are interested in simulation involving fluid flows in a variety of environments. I mentioned about jet engines, so this is the inside of one of these combustors, so this piece of the engine here. And you're looking at temperatures. This is a combustion chamber, so you're looking at injection of fuel, combustion, and the flame actually that is generated. This is instead a simulation of the external aerodynamics on the wing and what happens outside of the engine and what happens especially during landing to make sure that the system is safe. Now, these are pretty extensive and intensive calculations. They require quite a bit of effort. They are very, very complex in terms of the physics because involve combustion, involve a number of physical processes, and they are large scale. So the complexity of one of these systems is such that these calculations are actually extremely, extremely expensive. So that's the basic outcome of what we do. How do we build one of these simulations? What is behind this kind of simulation? So the process is relatively simple. So what the engineering simulations are really mathematical models. So they are computer models. And they try to imitate as close as possible real-world processes. In that case, for the engine would be a combustion process and the simulation of a turbulent flow and other physical disciplines. But the key that I want to point here is these high-consequence scenarios. And the reason I'm adding this is just to distinguish between something that just looks good versus that something that is actually accurate or is as accurate as you can make it. Because if you're making decisions, and decisions regarding financial decision or health or safety decisions, you want these to be really accurate, not just resembling accuracy. And so what is the process? We typically start from what we know, experience. Perhaps we built one of these engines before, or we have some prior knowledge about the physical process involved. We lay down what are the physical principles. We know that the law of the physics are pretty well understood. Conservation of energy is a principle that lays behind sort of system, all these systems. So we can build, based on those systems, these principles, some sort of a mathematical, theoretical model with some simplification. Typically, these are partial differential equations, but there are many other principles you have to include. For example, what is the description of the fuel, right? Is it a gas? Is it a liquid? These kind of physical processes. After we've done all that, the next step is to build a computational model, typically an algorithm, that finds a solution to the equations that we wrote down. And then these algorithms tend to be quite intensive, so nothing that you can use pencil and paper, write down the solution. Typically, how you compute a solution is to use a supercomputer. As I mentioned, these are very intensive calculations. We typically use thousands and thousands of GPUs to actually perform one of these calculations. But the final result is one of these sort of outcomes. Okay, so that's sort of the process we go through. And independently of what is the physics you're interested in, independently of the application, this is typically the process we go through in engineering or computational science in general. And so that's a fairly well-established system, well-established process. Is also a very time-consuming, requires very sophisticated skills to sort of manage the entire system. There is obviously the physics, the mathematics, the computer science, the computational science, and then eventually sort of the analysis of these results. Now let's switch gears. So this is what engineering simulations, at least the ones that I'm familiar with, look like. Let's talk about data for a bit. So first of all, I think you might agree that data is everywhere. Let me just be more specific. So if you think of the web, there is an enormous amount of data in the web, right? There is news, there are images, videos, all sort of data, and this kind of data is increasing, is growing exponentially. More and more data will become available, and there will be more and more opportunity to use that data for some purposes. Now, this is perhaps not a very engineering, type of data, but it's not only the sort of abundance of data is not just on the web. There is very much more and more. There is very much of an increase of data available in engineering system because of development of sophisticated sensors. So this is one really interesting example. These are again jet engines from Rolls-Royce, and how much data they generate. Okay, so let's talk about these numbers. So they generate 20 terabytes per flight per engine. What are these 20 terabytes? These are temperature data, perhaps accelerator data. These are all sensors embedded in one of their engines, right? Now they have two engines on a plane. They typically have, this is the number of flights in the United States per day, and this is typically how many hours each flight, and this is how many days per year. So this is how much data they have in terms of only engines, only from one producer, Rolls-Royce, running a year in actual flight data. Okay, and this is terabytes And this is billions of terabytes. So there is an enormous amount of data, no question, right? And this is just one application. You can think of, Tesla cars, right? There are, a number of sensors on those cars, and they generate data continuously. These are real physical world data of an engineering system, right? An actual sophisticated system. In addition to this, there is data coming from both computations and laboratory experiments. I showed you some of the calculations we do. That generates multiple terabytes of data per calculation. And experiments start to do the same thing. They generate an enormous amount of data. So there is no question, data is everywhere. The next question is data everything? Okay? And that's an interesting question because, in the early 2000s, there started to be a movement where the claim was that you just need data. You don't need anything else. You don't need physical principle. You don't need prior knowledge. You just need data, right? And so, in fact, this was a very interesting start of an article on Wired that talked about maybe the end of science because, again, it's going to be just data, and there is going to be no other way to get information. You just need data. And in fact, there were a lot of studies even in the later years where they sort of anticipated discovery of physical models and physical theory and principle and so on directly from data, right? Including discovery of things that we already know, like the equation of motion for fluids, which obviously we know. But there was, sort of a more and more of a attempt to just discover them directly from data without going through prior knowledge, right? Now, as you will see, I will argue that actually, it's not as easy, and that's why I have a question mark there. But I do want to point out that this was sort of a very aggressive sort of move from the data side towards covering everything that you can with data-based models. So let me finish this introduction by talking about this age of data. Why am I talking about age of data? And it's not just because we have data. That would be too simple. It's not that we are in the age of data because we have data. We are in the age of data because together with data, we have two other important components that have been developed over the last 15 years. The first is new architecture, computing architecture to perform computations with data. Okay? We didn't have, GPUs before, accelerators before. We didn't have, dedicated machines like TPUs from Google, and there are more that are emerging every day, that are hardware-specific machines that do computation and data extremely fast. Okay, so that's a key element, and again, now it's readily available. You have GPUs on everything. Every laptop has GPUs, and GPUs with data algorithms are extremely fast. Now, that's not even it. There is more. The third element is software. We have tremendously advanced software that is produced in a very highly sophisticated, software engineering sense from Google, from Facebook, and so on. And this is all open source. It's all available, right? So there are no barriers. Computing is cheap. Some of these GPUs are relatively cheap, with respect to the performance that they have. Data is cheaply available if you think of web data, and software is easily available, okay? And so it's the combination of these three that really means that we are in the age of data. And in fact, there have been applications that were just being spectacularly successful, right? Because of the use of these three, in facial recognition, video games or games actually, in speech recognition. These are incredibly sophisticated solutions that just emerged in the last decade because of the convergence of these three. And so just to point to a simple example, one obviously very, very known example is synthetic faces or deep fakes, as someone called. So these are examples from Google, how the quality of these images improved over time. And notice that these are not real people. These are virtually generated images. And the algorithm development has been sort of behind together with the development of faster machines and better algorithms and so on. And this is becoming better and better, and it will continue to get better. These are actually fairly old results. And so it turns out that maybe it's important to sort of think of what are data-driven models compared to sort of engineering models that I mentioned before. So what are these? These are statistical algorithms. They are statistical, so that's a critical piece to keep in mind. We'll talk about that afterwards. They learn features from data or extract features from data, use them to produce new data. This is a very, very general sort of description of what these algorithms are. And there are literally thousands of different versions of these algorithms, so there is not really one single algorithm. But the strategy is like this. You build sort of a set of, a data set of example phases. You pass them through a statistical algorithm written in one of these software packages, say PyTorch. You perform calculation on a GPU, and you train the algorithm. That's the type of, and you produce a new phase, right? And that's, is the process that you go through. There is no real specific requirement that the algorithm that actually understands that these are phases or what kind of features you're extracting. In principle, this can all be sort of automated. And as I mentioned, there are many, many successful applications. So let's talk about then a different paradigm for simulation. Maybe we should avoid sort of all this trouble and just use directly this type of strategy to build our simulations. So how do we do synthetic simulations then? Well, a simple way would be to build a database. In this case, I'm thinking of different geometries, the blue ones here, and I want to know what is the flow that goes around those geometries. Think of an airplane. In this case, they're obviously very, very simple geometry. These are sort of the velocity corresponding to the flow over those geometries. So red is small velocity in the wake. The object is sort of blocking the flow, and so on. So these are now this is my sort of quote-unquote phases, right? These are not phases, but they are flows. I can build an algorithm, in this case, again, using Keras, one of the open source software. And then what I can do is, the algorithm takes these geometries and takes these images and tries to reproduce them, right? So it's trained, so it's learning basically how to take a geometry and give me one of these velocity plots, okay? And so the training is simply going through all of those thousands of geometry, very much like I was doing on phases, like they were doing on phases. And then the idea is, what happens if I give it a new geometry, a triangle that was not part of the training set? Well, it turns out that the predicted output, so the output of this algorithm versus this, the synthetic versus the true, is actually very close, and it turns out it's actually very, very small, the error in this case. And I can generate very, very, large number of images in very, very small time at this point, after I train the geometry. I train on this. So it seems like this is possible and it's doable, and it's very much in line with what I was showing you before. But there are some challenges in synthetic simulation. The first one is that building the data set is expensive. It's not easy. It's not like I go on Google and I just extract 1,000 new faces from movies or other things that are already there. I need to actually perform each one of those simulations with some sort of care and attention, right? Because otherwise the simulations are wrong and I'm not learning anything useful. So it's not easy. The second is training the network is not as simple as it looks, especially when you have very large set of images, perhaps three-dimensional objects that you care about. And also it's not easy to select which algorithm. I showed you in that plot with Google that they had a different result every year. It turns out the algorithm was completely different every year. So it's not that it was an adjustment of the previous algorithm or more data. It was just a completely different approach. It turns out, as I mentioned, there are literally thousands of different algorithms that can give you this kind of results. So knowing which one to use and how to use it is really a difficult skill to learn. And then the other thing is that these are statistical methods, as I mentioned before. The accuracy is measured in average. The accuracy is not based on a principle. I'm implying conservation of energy, and I know that if that's correct, I'm guaranteed certain properties of the solution. In this case, it's all statistical. There is a training error, meaning you go through those phases, those initial data set, and you compute an error. What this means is that if you look at locally in one of these solutions, for example, at a particular location, the error might be very high. So even if average error is much less than 1%, the local error might be 5%, 10%. And there is no way to know in advance. Okay, so that's a pretty problematic issue, especially if you don't really look just, oh, they look very similar, looks about right, but you want to know quantitatively what is the velocity in this location, because that's an important quantity in your application, right? That's not something you can control easily. There is also something else which is extremely important in this setting, which is what happens if I train on geometries like this, so one single object, and then I try to do a simulation of two objects. Right? My synthetic model now has never seen two geometries. I've always seen one. Right? So I'm extrapolating something that I learned here in this case. The geometry now is similar, but there is perhaps interaction that that the algorithm never learned about. And so we actually tried something more, more cases just to see what happens. And it turns out if you look at the synthetic output, and you know a little bit about fluid mechanics, well, this looks about right. Even if I never trained on any of this combination, it's not that it's giving me a completely wrong answer, right? So it's qualitatively okay, but what about quantitatively? Well, this is the true solution, and if you start looking at it, well, it's difficult to say if they're accurate or not. Actually, they're clearly not, but you wouldn't necessarily dismiss this solution. So the issue of credibility and accuracy of this synthetic calculation is actually extremely challenging to sort of guess. You really need to be extremely careful in quantifying the errors. And the problem is that if you need to compute the true solution every time, then it's useless. Right? And so it's a very, very difficult assessment to do in this case. And final is that, as I mentioned, the details are not easy to grasp. What are the details behind sort of a model like this? In our case, these are the details, and I'm not going to go through the details here to tell you what this means, but there are a lot of things that you need to know if you want to produce this result. And actually, we started from a paper from a few years back from CMU, from Carnegie Mellon University, where they tried something very similar. And it turns out that their results are actually quite different and the details are not clear. So even if we started from there, try to reproduce everything, we ended up with something very different and we don't know why. Right? So reproducibility is actually extremely challenging in this case. So that's perhaps a good sort of introduction to data-driven models from a perspective of this kind of application. As I mentioned, in other applications, these might not be as critical as issues. So bottom line is that it's not easy to just go from here to here. Now, philosophically, one thing that you need to keep in mind is that there is something behind these two approaches that is very well understood from a logic perspective. So what is it? In this case, you're following what we call a deduction process. So we are going from theory to data. We're generating data based on theory and hypotheses we're making on that theory, right? If these hypotheses are correct, this is the solution. This is a completely different approach. It's an induction process. So we're going from data to theory, right? The data, the examples, the evidence builds the model that then produces new evidence, right? So this is a completely different paradigm. So it's not that you just, you swap one from the other. Even mentally, you're making a completely different picture of what you're trying to approach with your models. And in many ways, if the assumptions are valid in this case, if those principles are correct, the outcomes are correct. Because there is nothing else here, right? Are the assumptions you're making to have that deduction that matter. If the assumptions are correct, the deduction is correct. In this case, it's a very different process. If you have sufficient evidence, then you can argue that the outcome is going to be correct because you're covering sufficiently what you're trying to reproduce that is just a matter of finding the right solution among the ones that you already have, right? But there is nothing about the assumptions, you know, the evidence, how much, what is sufficient is very difficult to quantify. You know, in a sense, it's very difficult to quantify if the assumptions are valid here too. But they're completely different viewpoints of this process. Okay, so let me step back for a second and tell you that engineering simulation and data together have a long history. It's not just, you know, now that we start to think about this. So you know, there are sort of a sequence of different methods. The first is validation. So we use simulation and data to compare. If you're in a simulation, you have evidence from some experiment, you want to compare them, right? And you know, quantitatively, you can just see how close they are. In this case, for the airplane that I was showing you before, you can actually compare them and see if the pressure distribution on the wing are similar or not, right? That's a blind use of data to just check the quality of your simulation. So, but that's a way to use them together. The second is the C word, what I call C word, which is calibration. Is something that, at least in engineering circles, you never want to do. What does it mean? It means that I take my simulation and I change something, some constant in the simulation, something about the simulation to match the data, right? So I'm not using blindly the data, I'm just using the data to improve my calculations. But the problem with that, and this is illustrated in this table, but without going in detail, what this problem is that if I do my calibration for an engine, and I change my model so that I reproduce experimental data for an engine, what does it say about reproducing results on an aircraft or a car? Right? The calibration without sort of a basis, and just, you know, changing something in the model to get good accuracy is not going to be very generalizable. It's not going to be very transferable. And so we can make calibration more principled by going to what's called inference. And in an inference setting, you do that comparison and you do adjust your model, but the model is adjusted in a way that is really probabilistic. You're saying that you might have very, very different amount of data for different configurations, and you try to do this match by minimizing over, you know, a large set of data, the difference between experiments and simulations and experiments, sorry, by minimizing this or changing those constants, finding the best choices in a probabilistic sense. Now, this is where statistics starts to come in play, because one of the challenges is that the data is never perfect. The experimental data or the real-world observation are always affected by some sort of noise, some sort of errors in the measurements or malfunctioning or limited knowledge of the experiments. And so there is some noise added to the data that makes this comparison or this minimization problem probabilistic, stochastic. And so in that sense, it becomes a statistical inference. As I mentioned already, machine learning is nothing else than a similar process, a statistical inference, just based on a different kind of infrastructure. So rather than simulations that generate results that you compare to data, in this case, what you're doing is that you're building a model that has parameters, typically millions and millions of parameters, and you're solving an optimization problem that's similar to what we said before. But again, the data that you're generating is not simulations, but is a statistical model, just some sort of algorithms, direct algorithms. In this case, a deep neural network, but can be something else. And so the basic idea is that this is not, you know, from a mathematical perspective, is not very different, right, from what we were doing before with statistical inference. And in fact, what is more common or more interesting today is that you actually combine the two things. You combine sort of a generation of data through a machine learning methodology, generation of data through simulations. You have constant in the simulation and parameters in the machine learning model, and you solve an optimization problem that tries to minimize both distances at the same time. So that the model, not, you know, at the end of this process, you have a model that is trained with some knowledge of what an engineering, sort of a physics-based simulation will give you as well. And so it's not, you know, it's a sort of a combination of the two ideas. So now, in some sense, though, the important thing is that I don't think the replacement of simulations with machine learning or with data models is really the right goal. In my perspective, what is important is to reset the expectations. So I showed you this plot before, and I was saying, are these results accurate? Do they predict real-world outcomes? What is really critical, though, is to think about this real-world scenario not as a fixed scenario. The problem is not if you can reproduce this case, because it's very likely that next time somebody has an accident, maybe even with the same car in the same place, the scenario is going to be a little bit different. It will go a little faster. The angle at which it sort of hit the other car might be a little bit different. The car might be, a slightly different model or older model or something like that. So the truth is that we don't care about reproducing this scenario. We care about knowing how close are, but also what is the sensitivity, how much things will change if, for example, there are 2 people in the car rather than 4. Or what happens if this car happened to have a previous accident that, perhaps affected one of the fenders anyway, beforehand, right? So what we care about is what is also the sensitivity and the uncertainty in the simulation's outcomes. And so one of the things we can do is to actually perform simulation with quantified uncertainties. And what does that mean? That typically in a simulation, we have to have inputs. So what is the scenario? What are the conditions? And then we can generate the outcome. Is this safe or not? And in real practice, in sort of engineering practice, we have uncertainties because of manufacturing, because of the conditions of that particular crash, for example, that affect our inputs. Our inputs are not completely well known. We have to think of a range of possible inputs. And we also use models. As I said, we make assumptions. In this case, for example, we assume that the behavior of the material, the plastic and so on, is known. But maybe that behavior is affected by age, by deterioration, by other things that are not part of our models. So we make assumptions, for example, on the turbulence, of what is the model of turbulence, what is the kinetics, at least in this combustion case, where we generate uncertainty in the model itself, and this means that the outcome is also uncertain. And so just to give you an idea of what that looks like, for example, I was showing you this combustor simulation at the beginning. It turns out that there is quite a bit of uncertainty in this application in terms of the inflow condition of the fuel. Exactly how much fuel is injected is not controlled perfectly. The temperature of that fuel is not controlled perfectly, and that might actually affect the results. For example, if we look at the centerline temperature, this is a combined result of the calculation. For example, these symbols here are one specific calculation, but rather than running only one, we run thousands of them by changing, for example, the fuel conditions slightly, right? And we see what the outcome, and we generate an envelope. Now, this envelope is the uncertainty in the actual temperature on this line. And you can see that now there is a good understanding of what is the sensitivity. There is fuel changing, or fuel condition changing, but the temperature is changing only by a certain amount of degrees. This is all normalized. But the changes are actually known and controlled if you do simulations this way. Similarly, in the other case, this is the wing that I was showing you before. In this case, the I should have said the uncertainty in this case is in the inflow condition, the condition of the cruise, right? The airplanes don't fly always in the same condition. It turns out we can identify with these, many simulations, what are the regions that are actually more sensitive to that. And obviously, in this case, especially in the region around the wing, you have more and more uncertainty. In other regions, for example, in this area, the uncertainty is actually very low, very small compared to the original solutions. Now, these are now simulations that use data not to change the simulation, but to inform the scenarios and the changes that you might need to consider in the simulations. A more sort of interesting way is what we are doing right now. So this is the SpaceX Starlink 7, one of the engines, and this is what you're seeing is the injection and the start of this engine, right? It's a pretty abrupt and pretty sort of high-intensity event that occurs. I'll show it once again. And what we're trying to do is to see if we can use a different way to ignite this engine, rather than what they use right now, which is a complicated system of cryogenic liquids and fuel, what we want to use is a laser spark. We want to just use a laser to start this engine. And the reason for that is because if the system fails, if the system did not ignite in this case, then you lose the rocket and you lose the payload, you lose everything. And it has to ignite right at that moment because that's the design trajectory of the rocket and so on. So what we want to use is a system that is lightweight but also very easy to perhaps assess in terms of reliability. And so this is the kind of simulations we are doing right now. We have a rocket combustion chamber. We use a laser pulse in a particular location, and you see that that actually ignites. Now, it turns out that in this case, though, there is quite a bit of uncertainty in the initial condition when you set the ignition, because this is a very complex mixture of fuel and oxidizer, a low temperature, low pressure, turbulent. And it turns out that when we do simulations, for example, again, thousands of simulations, in this case we're not doing as many as already because of very complicated simulation, you see that in the same nominal condition, these 8 cases, some of them ignite fairly quickly, some of them ignite a little bit later, some of them did not ignite at all. Right? Just a change in the initial condition of the mixture is enough to lead to a different outcome. Now, it turns out experiments show the same thing. This is a comparison experiment in the lab that shows 3 nominal laser deposition that are the same, but again, 2 of them will ignite and 1 does not. Okay, so what we're doing right now is to try to build engineering, simulation, and data together, combine them, to build a physics-based and a data-informed model that can estimate what is the probability of successful ignition. So this is how we're sort of thinking, rather than replacing simulation, we want to use both to build a model that is accurate and predictive and fast eventually. So I didn't give you any of the technical details, so if you're interested, I'll share the slides, but there is a paper a couple of years ago on turbulence, and also the website of this project that tells you a little more, quite a bit more about the project. So let me finish by giving you my final thoughts here. So the first thing is why we're on the edge of data. I sort of explained this already. It's not just the data that makes this the edge of data, but what is the difference with engineering simulation? The way I think of it is that you somehow need to include physical principle in this picture if you want to be able to use data in the same way that you use it for other applications like finance or facial recognition. So that's the first thing. So obviously, because you're using physical principle and you're using simulations, and these are, again, open source simulation software, then also the computing becomes more complex. So in terms of complexity, certainly is more than many of the applications that are successful today, but there is definitely a path. And in many ways, the way you should think of it is that the idea is that these two should sort of go together. It's also nice because one is a deduction, the other is an induction. So it's sort of like there is a clear feedback or back and forth between the two strategies. So using them together makes a lot of sense in terms of sort of improving on what we were doing before, or sort of not ignoring what we have done before. And so this sort of leads to my real definition of what is engineering simulation in the age of data, which is mathematical models that represent real-world processes, not just imitate them, in high consequence scenario, but with quantified uncertainty. So that rather than just comparing outcome this way, you actually account for uncertainties that are present in the real world, because there are always uncertainty in the real world, in the simulations as well. And so you have a way to inform decision, not just by using one single simulation, but a sequence of calculation that help you build that. Now, I want to leave you. I don't know how much time I spoke, probably enough given that we were late. So I want to just stop by giving you a couple of final thoughts. Let me start from the past, because it's always useful to go back in the past and connect what we talked about to things that perhaps have been known for a long time. So I talked about synthetic phases as a success story for machine learning in the last decade. There is actually an example that is 150 years old. And in France in the 1800s, somebody, and this actually is photographed, but there was a sort of a lot of effort on this front to try to build the average, in this case, the average mathematician, how an average mathematician will look like. So what they were doing is basically painstakingly taking images of people going to a congress, putting them together and sort of combining those images into a single picture. Right? These are exactly what they look like if they do 12 or 31. Right? The numbers are very small. Any of these training includes perhaps millions of faces. Right? And this was done by hand, one by one, adding and computing the average rather than a much more complex statistical combination of those. But nevertheless, this is not a new idea. And the reason why they wanted this average mathematician is, actually the real goal of this was to identify traits that will lead to particular diseases. So if they take images of people that have specific disease, maybe they can find how a person that will develop a disease will look like. Right? So the concept was completely clueless, but still, that was the idea. Right? And so machine learning is not magic. It's really, I don't want to say simply, but it is statistics plus computing. That's the difference between these two is a more advanced concept in statistics, not just the average of images, something more, and a tremendous amount of data and computing. Right? That's the difference. So that's something to keep in mind. There is a lot to learn from the past. The other is this sort of challenge on reproducibility. And the key here is that these data-driven models are fundamentally dependent on the data. So a data-driven model is not just a model. It's a model plus the data that was using for training. Without that data, you get a different result, even with the same model. Right? And this is a completely opposite to what we were saying before about the theory. Once you have a theory, you have a theory. You write it down, that's the theory. Right? It's not that it depends on anything else. Doesn't depends on the assumption, but nothing else. Right? Here, the assumption, in a sense, are the training data. You need to carry that if you want to reproduce the results. And one example from the past here is actually much, much earlier. This is 3000 BC. It turns out Sumerians had a lot of mathematical sophistication. So these tablets actually reports in the front the average total grain production over 3 years, right, in a particular region in their kingdom. And it turns out in the back of the same tablet, they had the actual individual contribution for producers. So you could actually check that just by turning it around and seeing the individual data, right? Not just the final result, but all the data were available in the same place. So think about reproducibility, right? You're carrying the result and the original data that were used to produce it itself. And so I think this is a key thing to keep in mind in terms of using these models. Now, let me finish by giving you, not a vision, but 2 examples of the future, how engineering and data can be used in the future. And these are not new results, new examples, but I think are important in view of everything that I told you so far. The first one is what's called digital twins that you've probably heard of. Right? What is the idea of digital twin? Is to build a computational version of an asset, in this case a power generation engine. And this is actually running virtually through engineering simulation and is updated through data that are coming either from the engine that is the exact copy or perhaps from other engines that are similar. And the basic idea of this is to be able to spot, for example, if something is going wrong or to schedule maintenance for that asset and so on well in advance of when things go wrong. And so you can do a much more careful check of that system. Now, in this case, the physics process is extremely complex, right? If you think of a system like this, it's very hard to even simulate. You need large-scale computation. You will have a lot of data coming in different sources. There might be vibrational data, might be acoustic data, again, temperature data, and so on and so forth. And again, these are high-consequence decisions. If I stop one of these power generation engines for maintenance, this is going to cost millions of dollars. And so that decision should be as accurate as possible. But this is a very nice application of engineering simulation plus data as we move forward in sort of sophistication. The other is kind of the other way around. In this case, we are talking about massive computations done centrally to reproduce a system. The other side is edge computing. Edge computing is the idea that you do computing directly on the product, right? If you have, I don't know, a fridge or your car, the car actually is a computer and is automatically managing the data that is generated on the asset, on the vehicle itself, to give you warnings, for example, or to drive, right? So in this case, we consider edge computing because the idea is that you don't have compute power elsewhere that is sort of very sophisticated model. You need something very agile, very simple that can run at very low cost, very low energy in a car, in an electric car, for example. And so what you need, real-time response. You need to handle limited memory, slow processors, perhaps. You don't have a large supercomputer. And you need very agile algorithms. But also, you need preserved privacy, so you don't need to worry about how to share data without having problems with privacy. You need to have computational redundancy. What happens if you have an autonomous car and the computer actually shuts down? Right? So these are issues that, again, are interesting because they use combination of data and computing, but in a completely different setting. So on one end, digital twin uses enormous resources, computing resources. In this case, you use very, very limited resources. And these are two, I think, interesting examples of that. So I'll stop here and thank you for your attention. And obviously, I'm happy to answer questions if you have any.
Yeah, so thank you very much. I won't host this part, so everyone that wants to ask a question, you can raise your hand and then here.
Let me ask you from a different perspective.
Yes.
So we have
Yes.
We're seeing a new role.
I think you can. Everybody can hear.
So we are professors. We face a difficulty of how to change the way we teach students about this new world, combining physics, which is very complex, with data.
Yeah, no, you're right. Actually, from a educational perspective, this creates a lot of additional complexity. At least in the United States, I don't know if the situation is different here. It's very common that engineering students don't study a lot of statistical sciences, right? Statistics is a sort of a forgotten discipline most of the time in engineering. And on the other hand, if you want to deal with this, statistics is kind of a first-class citizen. You need to have sort of the background knowledge and so on. As you said, this creates complexity because now you're adding disciplines on an already full set of a curriculum that is already heavy and complex and so on. So I think that's certainly a challenge. But on the other hand, there is a tremendous amount of information that is available. And so I think the way I think of sort of our role is to guide students or guide their curiosity. Because again, you can find short courses on machine learning on the web for free everywhere. And so how you can help students sort of drive on their own perhaps some of the curiosity that they have in things that are useful, or embed some of these elements into classes that before didn't have it, for example. I think is the way we can do it. But the challenge is that knowing all these knowing everything that we want them to know for, say, engineering in aerospace, plus all you need to know for data science is actually quite challenging. But I think on the other hand, the opportunity is enormous. The value that this can bring to them in terms of how they approach problems. And in fact, I think this idea of deduction versus induction, I think at least, again, I speak for what I know in the United States, I think there is very little understanding of even the difference between these two processes. And I think to be a really good, knowledgeable engineer, I think you need to master sort of both viewpoints and understand how, what's the value and what's the merit of each and how to use them.
Okay, more questions?
Yeah, your talk was very general, which was
Yes.
the idea. But can you comment a little bit on some specific tools of machine learning that you think is promising you're using with success in your applications?
Yeah, you're right. My talk was extremely high level, and part of it was sort of to make sure to appeal at least to everybody in terms of the general ideas. Now, I would say there are, in my group, one of the things we're focusing more are methodology like autoencoders, for example. So specific technology that allow to extract knowledge from data sets without intervention, without human intervention. So one of the challenges is that, for example, if you want to recognize images, and you know the typical idea of cat versus dog, typically what you do, or one of the strategies that has been used, is to have a human, a person, actually looking at this picture and label them, right? Saying this is a cat, this is a dog, this is a cat, this is a dog, and then the algorithm sort of uses this information, the images plus that label, to sort of get a score and then eventually learn how to distinguish between the two. It turns out in the simulations we do, if you think about one of those engine simulation, these are three-dimensional time-dependent flow field that generates terabytes of data. And we actually don't know what we are looking for. It's not that if I look at every single movie of that, I can really learn what is the difference between this particular engine or that engine or this ignition scenario versus that ignition scenario. And so what we try to do is to build systems that are called unsupervised. So machine learning methods that are unsupervised, that don't require a human to label what is cat and what is dog. And one of these is autoencoder. One of these methodologies are called autoencoders. And that tends to be an interesting approach, but then the question about autoencoders is how to embed physical principles in a way that is credible and in a way that is generalizable. And that's the part that we're working on, sort of struggling like a lot of others, actually. Yeah.
I'm sure that you have thoughts and work on this, but my question is, you talk about the reproducibility of these models. And sometimes if you, for example, we have the conservation laws. If we force the conservation, just the conservation laws, we may reach to the trained models that we can reproduce with different, almost different databases. Have you considered this or not? Because, sorry, in the previous presentation you talked that you considered the simulation as a bunch of images.
Yes.
Okay, and I agree that if you if you consider that as a bunch of images, then you will have an image which looks like the real solution, but the magnitude of the, for example, velocity is not same. We are just witnessing similar contours, for example. But maybe if we just consider the basic physical law, conservation of, I don't know, mass, and put it in the loss function, maybe we could reach to better.
So it's a good point. I think the case that I was showing is a sort of a worst case scenario where you basically hope that just by learning you'll be able to get results that are credible. But the issue of reproducibility that I was mentioning there was more about transparency, maybe, of being very, very clear of what is the construction of the architecture that you're using, what is the method, what is the, because unfortunately details matter. Right? I would argue that it's true. Maybe adding some constraints in the loss function in the way you train might make the results more robust. But still, if I read a paper and try to reproduce the results in that paper, and that paper avoids or doesn't really explicitly describe certain aspect of the algorithm, it's very likely that even with the same constraint, I'm not going to get the same results. Or if the data is not readily available and I use a different set of data, it's not guaranteed that the results are going to be very similar. Now, and so my case perhaps was an extreme case, was intended to be more of an example rather than the standard practice. But I think the issue here is that when we do simulations, engineering simulation, physical simulation like you guys do, typically, you can actually write down exactly what is behind the algorithm in a relatively concise manner, right? You can, 5, 6 items, and you basically describe what you're doing, right? Again, the details might be slightly different, but it won't matter too much. Here, to really describe what you're doing, you need a lot of details. I think that's really the problem, right? That is the amount of information you have to provide together with your model so that somebody else can reproduce it is way larger. And that's one of the, it's not a showstopper, it's a warning, just to be careful that now the model includes much more information that you need to be able to share so that somebody else can use it.
Well, thank you for your presentation. It was very nice. My question is more of a philosophical question, you know. I mean, you showed us the face of the average mathematician, okay? There is a very interesting history. By the end of the 19th century, people trying to find the face of the crook, the bad guy, you know? And they took many pictures of assassins and thieves and bad guys. So, but what came up, what they obtained, was a face of a very good-looking guy, very beautiful one, you know, because all the asymmetries were wiped out, you know. So I think that there is still room for some modeling, you know, because you showed us the face of the average mathematician, right? Maybe it's not the average mathematician, it's the face of the average man at that time. Yes. So the results need to be, we need to understand what we want and what we obtain. And it's a kind of a model, you know? So we need, in order to analyze the data, we need some kind of model in our minds. And it happens for, as you said, face recognition and other things. Do you have something to say about that?
Well, I don't have much to add. I agree that the whole premise of trying to build up sort of the look of, say, a crook or a mathematician in that case, I think is faulty as a premise, right? The premise itself is faulty because we, from a practical perspective, certainly the average, and there is no correlation, right? It's not that because you look like that, you are going to be a crook. I mean, that's really what the problem is in that case. But I use that example just to illustrate the fact that you cannot simply rely on, rather than 12 or 30 images on 10 million images, and rather than doing it by hand, just use a big computer, and now, with that algorithm, you'll find the average mathematician, right? The point is exactly what you're saying. It's not more data and more computing will give you the answer, right? It's more that you need to formulate the question in a proper way, and you need to understand what is the evidence that you're bringing there to make that claim. And I think the basic idea is that these models are not causal per se. Just the fact that they generate a face doesn't mean that that's a person, right? It just simply means that the algorithm can take a statistical, not an average, but a statistical combination of all these and give you something that looks like an image. And that's not, it's not, much more valuable unless you have something to back it.
Well, again, thank you very much for the nice presentation. I'd like to ask about these differences you mentioned about the simulated and the data-driven results and both combined together. And when we see something like that, so you are burning some fuel and getting some jet engine to work, you can use the model, the data-driven simulation and so on, but you get some results, and you are reasoning, are they that different or not? But are this difference is not also related to the, let's say, time scale I'm looking at. Because if I want to know something very average, like thrust or fuel consumption, and otherwise in very small scale time, like say vibration or maybe some kind of fluctuating pressure that will lead to a failure or something like that. How can I combine this similarities or not? Are both models reliable for both time scales, for both, let's say, time or spatial scales, or are we not talking about, let's say, averaging the mathematician and averaging the jet engine? How can I deal with that?
No, that's actually a great question, because in the example of the rocket, I didn't go into a lot of details, but in the example of the rocket, the simulation, because of the cost and the complexity, can only simulate a very, very short amount of time after the laser pulse, right? Imagine that you have this, system, you just simulate a microsecond of it. Now, it turns out to know if the engine is working properly, you might need to wait 3 seconds. The first 2 seconds is still sort of ramping up, and we just don't have resources to simulate the entire thing. Actually, the idea of combining is that the experiments can actually take 3-4 seconds of that sequence and collect data. So but they can only do few. So we can do hundreds of simulations for a very short amount of time and tens of experiments for several seconds. Right? So that's what we're trying to combine. Very, very different time scales, but with the idea that once we have variability at the small time scale, together with the experiment, we can extrapolate the behavior of the system at a much longer time scale. But certainly, as you said, if your goal was to do a time average picture, then it would be a very different algorithm, a very different challenge to do. But the idea of time dependency, especially in problems like that, where you have a system that is behaving in a certain way, and then you have very large energy deposition because of the laser, you're basically completely distorting the system. It's going to go in a completely different trajectory. And so you need to understand for quite a bit of time what is the attractor, what is the new trajectory that the engine is going to. And those simulations are extremely, extremely expensive. So we can't really do it brute force, and we try to use data to help complement the data, complement the simulation, basically.
Thank you.